have class from 11 to 1, and then have activities at 2, right? And furthermore, I asked, and that day we cannot have class. So I would like to propose make a 3-hour make-up class at some point. So something like reviewing, maybe for at least 2 hours to make us those classes, because otherwise it's going to be a lot of class time lost. You understand? So at the end we'll talk about that with the calendar in hand. Okay. I'm going to do some problems to practice counting, and then I'll introduce more concepts. So, okay, English corner. Who hasn't been? Okay, Christian. Okay, so problem 5. Problem 5. So here we have a 3-digit number, right? I'm assuming that this 3-digit number is of the form ABC, where A is not equal to 0. And here we have several questions. Repeated digits. Your comments have been recorded. So, how will you do? Yeah, today I'm in a asking mood. So, how will you do? How will you do this problem? First of all, it is obvious that order matters, right? So they must have some repeated digits. How many repeated digits can they have? That's the very basic question. And well, one repeated means 2, and 1 or 2, right? So it could be of the form x, x, z, or x, x, x. So one repeated. Right? So let's count the first group. Ideas, mass, gang of professor murderers. Ideas. Good evening. Ideas. Use your brains. How many cases can I have when there is 2 repeated digits?
9.
Sorry? I can have the repeated digits here, right? And there's something else. Well, this symbol is different from x because 3x is this case. Right? I just have this. And then I could have this. Right? So how many cases can I have here? Sorry, say it again.
If x is 1,
Yeah. Okay, can I have 0?
no.
No. So I will have 9. So 9 for this x, how many for this symbol? 8. 9 or 8?
10.
Okay. Who said 8?
9.
9 why?
Because 9.
Because now I can use 0,
Yes.
right? So it is not 8, but I cannot use my previous digit here. So this is 9. Get used to say your answer followed by because and an explanation. Will be much appreciated. So here, the same, yes, 9 times 9, and here 9 times 9, and yeah, objection. Okay. Wait.
The circle wouldn't be 0.
No, because I rolled 9. Yeah, it requires a little thought. Here I have 9 possibilities because I can't use 0.
Okay.
Right, and then I cannot use the previous digit here, so it's 9 times 9. So, and for this case, how many possibilities do I have? 9, because again I cannot use 0. So 9. This was product rule. Yes, Paco?
In the
First.
if you can use 0 and you can use 9.
Here. Here. Here.
Yes.
Here I have 9 possibilities.
9.
9 because I can't use 0.
And the other numbers minus.
Yeah, yes. For example, I can have repeating digits. Or I can have that one. Oh, sorry.
But you can use 0 and
I cannot use 0 because it is a 3-digit number. In the sense that it goes from 100 to 999. Right.
no. Ya no puede ser entero, pero no puede ser otro número. El otro número entonces sería 8.
I mean, you are talking about this case.
No.
Oh, sorry, this case.
Yes.
So the first one. The first one could be anything except for 0. So, for example,
And the other number. No?
we are analyzing this case, right? first, this is this symbol. So here, say I write 3 down. And then I must put 2 numbers there. And they must be the same.
Or other number.
Yes, but not 3.
Yes.
No, because here I said just 1 repeated digit. Not everybody the same digit. And now, finally, that's a very common mistake, that you double count things. I separated things into 2 cases, right? When I have 1 repeated, right? But this must be different from this. Otherwise, you have everything repeated, right? So that's why I said 9 times 9, 3 times, and finally 9. So this was product rule. Those cases are disjoint clearly. Yes, please.
Pero la X sí que puede ser 0.
No.
No.
Not at all. That's why you have 9 all the time.
Pero si la X no puede ser 0 y el 0 tampoco puede ser 0, eso sería 8 veces.
No. What case are you talking about? This one?
¿Cómo?
Are you talking about this case? So this X cannot be
Sí,
0. So I have 9 possibilities, right? And here, for this symbol, which is not 0, just another symbol from X.
Pero puede ser 0.
Yeah, it could be.
Ah,
It could be 0. Yeah, I can have zeros at the end of my number, but not at the beginning. So, product group here, those cases are disjoint. So here, some group. And okay, yes,
I
please.
don't understand because
Why?
you say that 2 repeat the
You are going to be right. Because you can have 1 repeated, but when you write here, you have 3 repeated. There is no repeated. Yeah. Thanks. Okay, this kind of problems implies some analysis power, right? You have to realize that you have 2 cases, and then you have to. The left bench is just talking too much. First warning. Do you like Big Bang Theory? Yeah, Sheldon. First warning. So, this requires a good analysis power. You have to realize that you have 2 cases. Then, for the second case, you have another 3 cases. There is an easy way to do it. You should check both ways always. The other idea to solve this is to use the complement, right? So I want to consider all numbers So here I was computing the complement of this set, right? I'm going to call U, universal set, the set of 3 digit numbers. So U, which is 900, so in this case, I computed this guy just directly. Right, so let's see. Let's see what happens if I compute. the cardinality of A. So, ideas? How to compute the number of integers with all distinct digits. How many possibilities for the first position? 9. I cannot use zero. So here I would say I have 9 possibilities. How many for position 2? 9. Because now I can use 0, but I cannot use the previous digit. And finally, here, how many? 8. So this is that was much easier than the case analysis, because I wanted to do the case analysis because sometimes you have no choice and you have to go to the case analysis. But when you face when you face a combinatorial problem, combinatorics problem, just check which one is easier to compute directly the cardinality of your set, or just the cardinality of the complement. Sometimes it's very, very easy. Very, very easy. Okay. More. Well, I'm skipping the rest of the problem because in easy we have covered already. It's about divisibility. This is easy. 7. And 20 students compete for a first, second, and third place in a literature contest. So, yeah, we'll work here on each. So first, second, and third. Yeah, some of these problems are a little bit insulting. So how many possible winners can there be? Okay, so first question, does order matter? Yes, of course. So, and second question, am I selecting the whole set? No, just the 3 first winners. So I have 110 for the first one, chosen independently from the set. So this is going to be parallel rule. This is an R permutation. Yeah, quite insulting. Quite insulting. Okay, more. I cannot do more. I need to cover more here.
So we will be allowed to use calculator?
No. Well. I'm giving you
Windows operation.
No. For the exam, you cannot use calculator. Sometimes I just write down the final result for you to check if you want to do it by yourself. But no, just leave everything indicated. Yeah, no problem. I mean, the point is not a number from your reasoning here. Okay. I'm sure that you, good student, have done this by yourself. It is already on your mind, and yeah. So next it was order selections. We have permutations and R permutations. Right, so the next thing is to remove order. To remove order. So the idea is, well, by the way, here we were using two concepts, lists and strings, and here I want to remove order somehow, right? So if I have a list, what's the corresponding concept when you remove the order? In a list, order matters, right? So if here I write 1, 2, 3, 4, that's a string or a list. If I remove the order, what do I get? Definition 1 of this course. A little bit different. A set, and another collection of objects. Definition 1. I mean, this is a mathematics class. It is an inverted pyramid. If you don't study the basic, you won't get to the advanced. That's a piece of advice. So, okay, here I want to remove the order. Let's see how to do it. Suppose I have 1, 2, 3. I'm going to list all the possible permutations from this set. So it will be right. Why 6? Because this is 3 factorial. Applying application of the product rule. 3 times 2 times 3 times 2 times 1, right? And now, if I remove the order here, what do I get? Well, I get this. So those two guys just go to here. Right? Because I'm removing the order. And here I have just one set. So here I have 3 factorial and I divide by 3 factorial. Okay, this was a very simple example, right? The point you should get is that removing the order is about division. It's not about subtracting. Sometimes people say, oh, do that. No, it doesn't work. It's not this.
Why is dividing?
Sorry?
Why is... porque se factorial.
Also division about grouping, right? When you divide, you group things. Well, that's what I'm doing here. I'm grouping this into just one group. I'm not taking out elements from the set of this here and just making a group, a class division. So in general, I have n elements, and I want to select R of those, right? An order selection of R elements from A. A has n elements. So here I have element 1, 2, 3, blah, blah. We know that's an R permutation. That's the formula. Another way to write it, a shorter one. Okay. And now I want to remove the order. So how do I do it? How do I remove the order there? By what?
N minus R factorial divided
No.
by...
How many positions do I have? Let's read the blackboard. R. So if I want to remove the order here, every permutation of this string must go to just one set. So I have this. This is with order, and now it's without order. Right? This number, we use several names, like binomial coefficient, I'll be using these two notations, okay, depending on the context. So yeah, very important thing now. Very, very, very important. So, as I told you before, sometimes people say, what are mathematics for? And because some of you don't understand why you should study mathematics. The first of all is because it shapes up your mind. Shape is a verb because it teaches you how to think. It doesn't matter if the objects we are teaching you are used in the sense that you'll use it later on in a company, in a firm. That doesn't matter. It's because it teaches you how to think. You need to think. Because you'll become someday, I don't know when, you'll become an engineer, a computer science engineer. And those are supposed to think, to know how to tackle problems. Right? So here I want to talk about combinatorial proofs. This part is in the book, studied thoroughly. Thorough, with great details. Yeah, this is a very strange word because it's one of those occasions where letter O is pronounced O. So combinatorial proof. What's a combinatorial proof? A proof that uses a counting argument. This is going to go in the exam. Therefore, you have a special marker to say, okay, he said it will go in the exam. So, for example, I want to prove the following formula. And I want to do it by exhibiting a combinatorial argument, counting argument. So, what's the definition of a binomial coefficient in terms of selections? Is select k elements set with n elements. Okay, so then how without order, right? To form a subset. Because subsets don't have order. Right? So basically, here I have my set with n elements, and I'm going to select a subset B with k elements. So once I take out my elements, what's left? Another subset, right? Which is exactly the complement. So how many ways do I have to select B? N, okay, how do you call this thing? N choose K. That's the way to read it. N choose K. So here I have N choose K, right? So how many do I have here? Well, for this guy I have N choose K, and for this guy I have N choose N minus K. So the idea is every selection of a set implies a selection for the complement. What's left after you select B is the complement of B. So that's why these two numbers are equal. Okay. That was a combinatorial proof. Then I'm going to give you the algebraic proof just for you to compare. So I'm going to write down the definition of n choose n minus k. It says n factorial, n minus k factorial. What do I have to write here? Show me that you can apply the definition. What do I have to write down between the rounded brackets? Yes. But this turns out to be k, because the n's cancel out. So oh, by the way, that's my proof, right? But if you get the other hand with this kind of proofs, you'll save lots of time in your exam, and also, this is deeper than this, right? Realize that every selection of k elements implies a selection of n minus k on the complement. Is much deeper than just carry out this little computation here. Right? The last one before the break. If you want to do this algebraically, that's very long. I'm going to leave it for you. But the combinatorial argument is really clever, and it's very much used, so pay attention to this. Again, I have A, n elements, and I want to make a selection, right, of a subset here, B, and B has k elements. It's a selection of subset, there is no order. Right? So my idea is the following. I'm going to fix an element in B, say X. Right? So all possible selections may have X or not. Right? So I'm going to count those selections having X and those selections not having X. So suppose I don't want X in my selection. Yes, Mario?
Let us fix X belongs to A.
Sorry. Yes. Thank you. So I don't want X to be in my selection. I don't want X to be in my selection. How do I count it? So B is going to be my selection. I don't want B there. How many? Well, first of all, what I do is to remove this one, right? So I'll have a new set composed of n-1 elements, right? So I remove this one. How many elements do I have to select? K, right? So the answer is K, right? But now, the other way around, I want X in my selection, right? So what I do is, first of all, I remove it and I put it in my selection box. It's going to be there. So I remove it. What I care about is for the rest of my selection. How many possibilities do I have for the rest of my selection? K minus 1, right? Because this guy is going to be here, then I have to choose the rest of it, which is K minus 1. Yeah, it's my formula. And that's it. That's a simple, deep proof. A simple yet deep proof.
I didn't understand anything.
Sorry?
I didn't understand anything.
Okay, don't worry. That's what I am here for. So again, I want to prove that a selection of k elements, right, out of n elements, as I said, without order, is the sum of these two terms. Right? So here I have my set A, perfect. I fix an element in A, any one. And now I make a selection. Okay, that selection can have X in it or not. Sure? So I'm going to, and both cases are disjoint, either it is or it is not. Okay, so I'm going to count when it is in and when it is not in. So when it is not in, oh, it's the other way around? Yes. Oh, sorry. So when it is not in my selection, right, what I do is to remove it. Just I put it apart. And I say, okay, now I'm going to select from here. Since it is removed, I'm sure it's not going to be selected. So I have n minus 1 elements because I remove x. Right? So I have n minus 1 here. And then I perform my selection. And I have to take k elements. Because of that, I'm sure that x is not going to be in the selection E. Right? Do you understand? Okay. That was the first part. Selection where x is not. Right? It's not in. And now I want that x is in the selection. So first of all, I remove it, but with the idea of putting it in the final selection. So I have n minus 1 possibilities, because x is already selected. And now I have to complete the selection. In order to complete the selection, I need to make a k minus 1 selection. So that's this term. And that's it. Now you sum both.
No, but
And you get the fourth.
if x is on B, why do you take apart x on
Because
B?
I'm going to make my selection, right? The first element is going to be x. I take it apart, but I put it in the box selection. It is already selected, it's there. You see? And then I have to choose the rest of it, which is k minus 1 elements.
I don't understand the n minus 1. Why?
Here, when
The x.
okay, you have n elements. Take x out
Yes.
and put it in the final selection already. Is there? So I look at the remaining set, and I have n minus 1. To select out of them k minus 1 elements. Again, my box. I take x. I put it in the final selection, and now I say, okay, I must complete k minus 1 elements. So I take k minus 1, I put it here, x was already there, and that's it. Okay. This formula is very important, and I give this place to Pascal triangle, which is a recursive way of computing the binomial coefficient. So here I have 0, choose 0. Here I have 1, choose 0. 1, choose 1. Okay, and the sum of these two guys, according to the formula, is 2, choose 1. Right? Just put here n equals 2 and k equals 1, and you get that. Then I have 3. Choose 0 and 3, choose 3. Those are always constant. What do I have to put here?
Eso estoy partido.
El del 2 no sería 2, 2, no sería 2.
Yes. Thank you. So, what do I have to write down there? Yeah, 0 and 1 must be the greatest. And here, right? And this goes to infinity. Okay, let's take a break.